Hello, everyone. So I'm going today to talk about how we can optimize Lustre for AI inference workloads, and thanks to Maurice. Maurice yesterday provided good information about what inference is and what key-value cache is and why it's so important. So I'm going to go briefly through the first part of my presentation. So our motivations, we are the guys who are trying to bring Lustre beyond national labs and universities, and we constantly are looking for new use cases for Lustre, and I believe today is a good chance because AI inference became the most dominated workload in enterprises, and the key question for us is, can the Lustre be the universal solution for AI inference today? Okay, let's go briefly through the first part of the presentation. So that slide demonstrates a brief sharp of typical AI model inference. So user requests something, the system can retrieve additional data from shared storage, from web search, etc. Then GPU inference runtime does attention mass and decode tokens, and GPU gets the model weights from the shared storage, and to optimize GPU time and to optimize some sharing parameters, it uses key-value cache. The same idea, but for agentic inference. In case of agentic inference, a single agent can call sub-agent, and it can call model multiple times while resolving some tasks, and each time agent runtime call model, it sends almost the same data from the previous steps, and this situation is so this move key-value cache over the existing HBM and local storage. So that's why we need shared storage for key-value cache. How the main terms, so the model is serving in two phases. First phase of prefill. On prefill phase, GPU calculates key-value pairs in parallel, and this phase is mostly compute bound. As a second phase is decode. On decode phase, inference agent generates one token at a time, and this workload is mostly memory bound. And because of, in case of multi-turn conversation, in case of agentic workflow, we have almost the same prefix for each prompt. We can store the prefix cache in some memory, in HBM, in RAM, or shared storage, and calculate only new data. This dramatically decreases GPU load on prefill phase. And this is a slide from NVIDIA. So NVIDIA proposed to do disaggregated serving because, as I said, prefill and decode are different workloads, and it's a good policy to split workloads on different devices and to share key-value cache between these devices by copying key-value cache or store it on some shared key-value cache engine. Everyone now talks about key-value cache as a main workload for inference, but it's not only one workload. In modern inference environments, you can see multiple models because you can usually modern enterprises use a couple of large models as orchestrators and multiple smaller models for each particular task, and you need storage to bring these models weights to the GPU accelerators. Also, of course, in modern workloads, and especially in agentic workloads, we need to implement RAG or some knowledge management, and also, of course, we need to store session artifacts on durable storage. So we conducted some research. We reviewed several papers for each workload, and so let's start from model loading and staging. And this workload is home turf for Lustre. Lustre is very good for this workload because we need to load multiple data in sequential manner with large block size, so it's read dominant workloads, which is very good for Lustre. The second workload is RAG. 3 years ago, I would say that Lustre is not bad solution for the retrieved knowledge workload, but 2 years ago, I conducted research and measured Lustre with under async I/O workload, and thanks to data on MDT pattern, I believe that Lustre can be very good storage for such type of workload, but it's out of scope of my presentation today. Control plane, session artifact traces. The problem here is it's gray zone for now because there is no sustainable demand from enterprises. The companies are still researching which type of data, how long they should store, and this workload should some additional time to investigate. And again, key-value cache, most popular term today for inference storage. So usually data split into several tiers, and the hot parts of key-value cache stored on HBM memories and DRAM and VML, and the remote storage is used depending on model, depending on serving engine, depending on key-value cache engine. We can see different I/O size beginning from 64 K to several dozens of megabytes, and for prefill phase we see mostly sequential append only, and for decode phase we mostly see large block read operations with some small portion of write operations, and performance according to existing papers can be from 2 to a couple of hundreds gigabytes per second for each instance. So the paper I found the most interesting, this paper from University of Amsterdam at IBM and University of Amsterdam found that the most dominant size of I/O was 128 kilobytes for read and write operations, and unfortunately they were not able to saturate SSD. And when I saw this paper, my initial idea was to use DOM to optimize performance on inference workload, but my further research demonstrated me completely different numbers and different figures. So I will show you. So I believe you saw this idea from NVIDIA. NVIDIA suggests to add one more layer between local SSDs and shared storage. This layer consists of external eBOFs equipped with BlueField-4 and CMX target, where BlueField-4 acts as a storage engine. So one of questions for me is, can we run Lustre in such the configuration? So this is quite busy slide demonstrating typical inference software architecture. On the left side, you can see inference servers and orchestrators, mostly developed by NVIDIA. In the middle of the site, there are multiple engines for inference. Each inference engine can have own key value cache, and the right side you can see different backends for key value cache, beginning from local storage and some kind of key value stores. And LM cache now became standard de facto for key value cache management, and it became one of the most popular solutions for key value cache management, and supports different types of backends. And in our further research, we will use LM cache as a key value cache engine. So our original idea looks like something like this. So idea here is to run our high-performance Opus engine on STX platform, allow us to provide individual drives and provide RAID groups across network. So, and to run on the compute side, Lustre client and server side on the same box. And the idea here is to utilize read-only persistent client cache to decrease east-west traffic between compute nodes, because for Lustre it's not too easy to force client to read mostly local OSS. So, and the Lustre should work as a backend for LM cache, which serve key value cache for model running on GPU. So a couple words about our Opus engine. What is it? So the main idea is Opus engine is high performance and very efficient storage engine, which can be run almost everywhere. It can be run on Bluefield GPU, bare metal, in virtual machine, in container. It works in user space, in transform multiple disaggregated storage into protected volumes, and it also provides some additional functionality like COS, ACL, etc. It can be enhanced with additional services like compression and additional checksum in future. So, okay, let's go to our test. I compared 3 different configurations. So I prepared Pseudo STX platform based on standard server equipped with 22 NVMe drives, and with the RAID Opus I provided volumes to the system running benchmarks, and I compared 3 configurations. The first configuration was based on XFS. I used XFS as baseline. XFS was formatted and mounted with optimized settings for large sequential I/O. And the second configuration was standard Lustre, where I put the Lustre client and Lustre servers on the same machine. And the third configuration was based on Lustre plus read-only persistent client cache. So I split all the drives into 2 groups. The first group was operated as backends for OSS, and the second group was operated as a caching volumes for ROPCC. I used ML per storage key value test. So I tried different models of different architectures. So I chose 3 models: Llama, GPT, OSS, and DeepSeek. I tried different workloads like synthetic chatbots, coding, documents, and pre-stored shared GPT, GPT traces. I tested under 2 scenarios. First scenario is related to bandwidth optimized, and the second scenario is storage stress scenario with almost no cache hit. And I also split all the tests into 2 phases: prefill only, decode only. And for solution with PCC enabled, I ran tests twice. So there are some fixed parameters. I set max concurrent allocation to 32. I have 1 trial per experiment because I had limited time. And also I have different number of experiments per each configuration. I had to exclude Llama 3.1 70 billion parameters because I made DIO kernel panic with Lustre here because of large DIO sync write operation. And also, as a last stage, I also excluded burst GPT because I saw no valuable data, and this workload requires additional investigation from me. So that's how each test was run for each cell. Okay, some limitations. Okay, of course, I run all the tests on unreleased software, and I used pending patch, which gave me 15% better performance, but it still has not yet been accepted upstream. Results was not submitted, so it was not externally reviewed, and I will going to demonstrate only most valuable experiments to you today. So I started from investigation of I/O profile, and here you can see very large difference with data provided by University of Amsterdam. So average block size on prefill stage was about 150 megabytes, and peak write size was close to 1 gigabyte. So it's more than one, it's close to 1,000 times larger size than University of Amsterdam investigated. For decode phase, you can see that average read size, block size was about several megabytes, and peak read size was about 23 megabytes. Unfortunately, I was not able to saturate the storage bandwidth, so as I said, I had two links of 200 gigabits, so expected storage performance was about 45 gigabytes per second, and even in case of peak bandwidth for read operations, I was able to get a little bit more than half of storage bandwidth. That's one more point to further investigation, how to saturate storage there. So let's go to the results. I looked at two main metrics. The first one metric is bandwidth. Bandwidth was measured in tokens per second, end to end, and from the storage. Again, we have two phases. The first one is prefill, and the second phase is decode. And here you can see that on the prefill phase, a Lustre slightly trails XFS by 50 to 20%. This is a payment for over suboptimal configuration, where we have client and server side on the same system, and we do not utilize Lustre parallelizations here because we have only one system in the data path. And thanks to read-only PCC cache, end-to-end throughput with Lustre was almost the same with XFS, which is 100% and slightly overperformed our baseline on XFS. So this is more detailed information here. And so for prefill phase, you can see that for some workloads and some models, the Lustre on prefill phase demonstrates almost the same performance as baseline on XFS, but for some workloads, Lustre is slower. But for decode phase, Lustre with PCC enabled almost the same as baseline of XFS, and of course, Lustre sometimes it outperforms XFS. More further, so the second metric is latency, and here you can see that for prefill phase, Lustre more or less the same as XFS, and for decode phase, Lustre with PCC enabled demonstrates almost the same performance as XFS. But without persistent cache, Lustre demonstrates up to 50% worse results. Okay, so I had the caching device size equal to the storage device size, what is not solution for real workloads. So I decided to find the best eviction policy for the key value cache. So what I did, I collected a lot of metrics I ran all the models again, but I changed a Llama model to 8B to avoid DIO crash, and I collected a lot of data and using strace, BPF trace, and in total I have about 280 gigabytes data of trace, and then I developed standalone cache simulator, and I replayed all the traces versus different eviction policy, and I used Oracle as a baseline and compared different eviction policy with baseline, and as a score I used hit ratio and amplification as the most valuable parameters here. So that's my results, and there is two very interesting output. First one, even with small fraction of cache size of 1% of total data, I was able with LRU and more smart eviction policies based on LRU get very good hit ratio. This is because of a small portion of key value cache was very hard, and calls of these parts of data provides the most of serving capabilities. And the second, you can see that LRU and more smart policies like ARC and 2Qs are almost the same. This means that LRU is quite good policy here, and more smart policies operates almost as LRU because of this workload is mostly recency based. But hit ratio is not only a parameter here. Another more interesting parameter is amplification. Amplification is how many data is actually served to the application in comparison how many data were pulled from storage to cache size. And here you can see that the eviction policy demonstrating the lowest result at the same time demonstrated the best result for amplification. It's almost 10 times better than ideal Oracle policy. So this slide demonstrated some hit ratio versus amplification. So that means we don't have any ideal solution, because if we want to be focused on hit ratio, we should choose one of basic eviction policy like LRU, ORC, or 2Q. And if we are interested in decreasing of amplification and decreasing of east-west traffic, we can use some TNLFU parameters. Also, I did some additional research tuning the two worst eviction policies. The main idea was that default parameters are not the best, but tuning didn't get any valuable results. So I have some numbers today, and today I can say that read-only PCC cache helps Lustre to provide very good performance result, even in comparison with high-performance local file system running across very fast NVMe fabric device. But I was not able to saturate the bandwidth of my backend storage, so First of all, I want to increase the performance capacity of the test environment, to tune some storage parameters, to tune some file system parameters, to tune some testing parameters to saturate the existing storage bandwidth. And at the second phase, I'm going to build true scale-out solution consisting of multiple OSS servers and multiple clients, and I want to compare all my cache simulation with real result in more real environment in future. And as a last stage, I want to run real workloads, so I'm going to add some real GPU here to run agentic closed-loop workflow, to deploy all the inference stack and collect all the data and compare this data with the results of synthetic benchmarking. So that's all.